Hi everyone, this is my lecture, my fourth lecture about the mathematics behind the coronavirus COVID-19. And in the last three lectures, I kind of talked about the population, and let's take the population in the city. And I said it's divided in three compartments. And I told you this is an SIR deterministic model. What is SIR? Susceptible people, infected people, and removed people. Removed people are people who can recover or who can die, and we want to prevent that. And I said there's a flow from susceptible to infected. People get infected, and that's the rate at which they get infected. Then people, they get removed. So that's the rate at which they get removed. If you want to see more details, please watch my previous lectures. And if we put all these three together, it's a system of nonlinear differential equations. Now to solve this, it's not very easy. However, you can do that by using different mathematical softwares, and I've done that for you, which we're going to go over in a little bit. So now I hear this question, when the peak is going to happen, because the number of infected people are increasing right now, and then eventually they're going to decrease. So that happens when the flow in equals to flow out. So that means that di dt equals to 0. Or in calculus, we say we have a max when the derivative equals to 0. So putting that equal to 0 and solving it, we can isolate this fraction, which is as over b should be equal to 1. What is as over b? That's R naught, the big R naught we hear every day. So it's to controlling this value who's going to control that peak. Let's go over this. What is R naught? That's the formula for R naught, and that's called basic reproductive number. In here, A is the infection rate. I talked about it in my last lecture. B is the recovery rate. I talked about that one also in my last lecture. Please take a look at it. And S are the susceptibles. So we have this fraction, and our goal is to keep that fraction low. Why to keep that fraction low? Because if more people are infected and the healthcare capacity is this line, then there is overflow. Hospitals will not be able to handle all the sick people, so we're going to have more deceased people. Now let me go over this one more time. A times S divided by B. This is a fraction. Our goal, make R0 smaller. How can we make that smaller? There are three ways. One is decrease S, number of susceptible people, and that needs vaccination. Question mark, not available right now. Increase B. What is B? Is the recovery rate. And right now, the average number of days that takes a person to recover is 14, so B is 1 over 14. It's almost 0.071. Please remember this number because I'm going to get back to that. So how do we increase B? Antiviral medicine, question mark, not available. Finally, decrease A. How do we decrease A? That's under our control. Social distancing, hand washing, wearing gloves, mask, that's how we decrease A. So coming back to R0, it's very hard to determine R0. I did some reading, some research, and some research from UCLA too. So in one of the papers I was reading, they said R0 is a number between 4.1 and 7.0 with 95% confidence level. And this is some statistics. So if I take R0 to be 4.1 and I solve for A will be 0.29. You'll see how this changes. if I say R0 is 7, then A is almost 0.5. I'll show that to you also. And if R0 is a low number, I heard that in some cities 2.5, then A becomes 0.18. Now, what I did, and I want to share with you, I wrote this little Mathematica code that helped me to solve this. I'm not a Mathematica expert, but I managed to get this. So let's look at those graphs first. So the graphs, just to show you, the orange one are the susceptibles. The black graph here is are the infected people, and the red one are the recovered ones. Here the y-axis I put from 0 to 1. Why did I do that? Because that shows a percentage of population. So, and of course these are number of days, and I try to do that from 0 to 360 days. So let's see, let's kind of analyze this graph. First of all, Mathematica has this code and this solve, so it's pretty nice. It allows you to solve this numerically. And the other nice thing about it is you can manipulate A and B. Change A and change B, see what happens. Now let me explain. B, as I talk about it, I said B is 0.071, 1 over 14, so I left B the same, 0.071. Now we can change A and see what happens. First of all, if I, let me just animate this. I want you to look at these little graphs, how they changed, and then how we can put them together. So let me stop this. Now, we won't touch B, but I want to make A1 maximum possible. So, and you can see, let's look at, so A is 1 in this case. Let's look at our graph. This is the worst case scenario. So if we did not do anything about this and A is 1, as you can see, about 70% of the people would get infected in a very short period of time. That means if the schools were not closed, the universities were not closed, then if probably less than a month, 70% of people would get infected. Now let's change A, let's make it smaller. So the second number I show on the board was 0.5, so let's go more. But let's keep it at 0.6. 0.6 again, this, as you can see that this peak comes down, it's almost 60%. So, and the number of days they have increased. So let's go to 0.5, 4, let's look at 0.3. 0.3, it's still less, 40%, and the number of days they have increased, about 50 days. So if we keep it at 0.2, let's see what happens at 0.2. So 0.2 is the peak happens in about 60 days. So probably 2 months after March 11th. However, do not count on these, are just my own calculations. I try to kind of predict this. So 60 days, however, this is 20%. And I heard that the hospital or healthcare capacity is at 10%. So we have to still make this lower so we have less infected people. So 0.1, well, the peak happens in, it's a dramatic change. So it's about 160 days. So right now, the value of predicted A is 0.2. So let's go over that one more time. So, and this is the graph we have. So the reason why the government official or the state officials, they tell us to keep the social distancing and they're not opening the schools and the universities, is just to keep the value of A low. I hope this lecture was helpful. Again, it's not what I did, it's just my own research on the number of days. I just want for especially my students to get kind of familiar with this model. It's a very good model that uses different types of mathematics. Hope I was helpful. Please stay safe, and I'll see you next time.